Thanks for coming, all of you. It's actually a privilege to see a full room. I was the first one to come here, which was a good thing to do. But seeing all of you here at this hour, sorry for a late start, but we'll hopefully make it worth your while. With that said, I'm a JVM guy and have been looking at Java problems for a long time, looking at how JVM scales, how things break when it scales. So everyone has looked at, and I've met a lot of you. How many of you have started Java before year 2000? And how many of you have started looking at Java in the last 5 years? Very cool. So there's a lot of Java has taken a lot of a very long journey over the last 15 years and 15 odd years. And on the server side, things have changed dramatically. Concurrency has become more prevalent, more modern, more required. You don't think about writing programs that have no threads anymore, right? So and then there were server-side containers that were abstracting most of this from us. What we have today is all of that logic is on your Eclipse, on your IntelliJ station. So you cannot ignore the constructs of the Java memory model. And for a long time, Java memory model was broken, and we'll see a little of that. It's luckily doing much better now in the post concurrent collections. A lot more good things have happened, but really, this is not a talk about big data. It's talking about JVM issues behind big data. And all the big data players are suffering these today. All Java apps have some of the notions of these problems, but specifically more so big data. And when I speak, thanks, Sasa, as a slide. This is actually a slide from, who remembers this picture? There you go. Yeah, Dr. Seuss, where the bottommost part of the stack is actually, he's called Mac, and he's basically screaming, dude, any more on top? Right? So the trail ahead, synchronized is the locking paradigm. That's what people have always been using. We'll double click what's happening behind synchronized. How locking is working there. We'll also propose ways to try and build collections that avoid synchronized. And some of you have looked at it if you've seen Brian Getz' book, Concurrency, you will actually see a chapter dedicated to that. But we'll just look at how to build a non-blocking collection if you had the leisure to go build one yourself, right? And there are some ready-made solutions that you don't have to build, but we'll double click on that. And so Sasa mentioned there's a possibility of a talk of internal JVMs. If I know whom he's talking about at Azul, Cliff Click, he actually wrote that collection. So if he's doing the talk, make sure you're there. It's a beautiful talk. So then you have collections, general collections, how they play, and we'll fast forward to serialization, UUID, and then to garbage collection. So the talk is going to be a little jarry because there are sections in it, and they're focusing on separate sections. So, but these are all the issues that we see on a daily basis when you try to scale your collections, scale your app. So, and then if you have any questions along the way that I've piled up, feel free to lift your hand, stop the flow of the talk. That's fine. A synchronous Q&A is fine. So I don't think we'll get to be able to talk about I/O itself, but hopefully. A call out to the tools of the trade. People looking at Java everywhere have, there's no performance or no metrics without a tool. Tools are the reason why we are here. Humans build tools. So there are different levels of these tools. So these tools are kind of ordered in order of how much impact they have. Towards the end, Z-Vision is your lightweight. At the top of this is you're looking at what your JVM is doing. If you want to look at what is happening while you're running your app. JConsole is a I'm sure everyone used JConsole. Visual VM gives you a view on how the GC is playing, how the various things, how the objects are growing, so on and so forth. How many of you have used YourKit? See, it speaks for itself. It's a great tool. ZVision is Azul JVM. It's a JVM tool. It's a JVM monitoring tool baked inside the JVM. So lightweight, so that's also less available. If you look at the JVM observation tools, TI, DI, and PI. Again, this is JVM tooling interface. So tools are not the ones that you get from tooling vendor. You can wrap one your own. The JVM TI, we won't go into the depths of it, but you can actually write a small tool that measures how your objects are being laid, how your allocation rate is. You can put a dash Java agent, and it will spit out those information to your logs. So some of the new big data vendors are actually doing that. So they put a small Java agent that measures your memory, stuff like that. So TI has traditionally not been exploited by end users. It's beginning to be a place where people are getting their hands dirty as well. What's the OS doing? Again, dtrace, oprofile, vtune, perf. Perf is actually oprofile very well packaged by Red Hat. So you can actually sudo apt get install perf, and you can actually see how what the instruction set. We'll see a few outputs of this. Vtune is Intel's Vtune, which also does a lot of deep dive of how your program is running, what your cache misses are, how you're doing your how the instruction sets are being laid out. One cool thing about Vtune that I would call out is you can actually run the program on your laptop and say, how would this run on a big 4-way Nehalem processor? So you can actually say, okay, you could do a map from, I ran it like this here on this Intel chip, how would it run in production, for example? So there are some interesting tools that, nuances that are brought to this by the OS guys and the hardware guys. So of course, everyone probably ran into Ganglia. How many of you use Ganglia or have heard of it? Sure, production monitoring. You can also send alerts from your program. If you're the people who are trying to do massively parallel programs, if you're trying to debug a Hadoop program, you can send a small alert through a Ganglia Gmon, and it would come up back to the main system, even if this program died. So that's something to look after. NAGIOS, again, another popular tool. Netstat, LSOF, yep, the list goes on. But these are kind of traditional, and we kind of expect people to be using those on a daily basis in production. Yep. This is actually a Matt Groening production from The Simpsons. Yep. Synchronized. It's an eye chart. Synchronized under the hood, when you do a Java lang synchronized, so if you assume whether it's in the function or inside the code, what's really happening is actually, so if you look at the top right corner, that's actually how your object's laid out, right? That's your object mark word. So on the left-hand side, you have the bit fields. You can say, based on what you store in the bit fields, your logic flows differently. So for the vast majority of locks, they're never actually contended. So you're basically racing through synchronized. Uncontended logs are cheap. So historically, people would say avoid synchronized like real dirt, right? But if your code does not actually contend, the synchronized is not so bad. You actually go all the way down, right? It's when you actually contend, that's when you see the first lightweight lock come in, right? And then, of course, you need to inflate the lock. That's when you see a big, heavy monitor. So behind the scenes of your synchronized, you actually have a monitor that's thin until it's actually contended. The first contention, then you see inflation of that monitor, and that's when you're actually seeing the effect of the overhead of a real lock, right? Now, what came about in the last few years, actually being able to bias the lock. Say you're a thread, you own this lock, and so there's very high likelihood that you're going to run through the code before someone else needs to get it. So the whole concept of biasing was quite expensive. The circa 2006, Detlefs and the Sun team came along with a store-free biasing ability to bias without a store. And the crux of that is coming at the last one. So if you store the thread ID, epoch, and age, it's a biasable lock. So you have a thread ID. So you're, next time someone is trying to pick it up, you're going to bias the lock to live with this thread and let it finish, let the other threads loop a little, let it finish, and you probably get to the end of the program before you need to actually swap the whole lock. So that's the fast path. So the fast path is no contention thin lock, and then you try to bias locks without, or you can, so, and then if it does get a contention, you actually have to force the thread to give up the lock, then you bulk rebias everything. So the crux of that has been that they achieved a store-free biasing by actually having a thread ID and an age. So and that's kind of the new nuances. And so for a long time, if people have remembered having used thread biasing or used biased thread locking, now it's a default in 1.6. So this is what's happening behind the scene of a synchronized statement. Needless to say, locks are expensive. If you have a highly contended program, locks are expensive. We'll see how that also plays into the Java memory model. So Java memory model historically, I mean, you cannot go talk about Java without talking about Java memory model. How many of you heard of the double check locking scheme? And how many of you have been told it's broken? I guess all of them, right? So double check locking came across where people have been taunting about lazy initialization of objects. And when you do lazy initialization, you want to make sure that for the odd case where you do need to fully make this object, you want to lock and make sure it's done in real time. Now, what happened in 06 was people, or 04 actually, Brian Getz and missing the name, they came about this concept that Volatile was actually not maintaining the ordering of threads. So in some sense, you were not guaranteed order, even partial order, within the program. So double check lock was broken, and so that was considered the most intact locking mechanism up until that time, when we suddenly realized that the memory model was not ordering things by causality. So if you look at this, so post 06, which is all the JVMs after that have been patched, is that you see that if you maintain partial order in this thread A, and then make sure at the lock transition everything else is also ordered, partial order in this way, partial order on the second part gives you global common order, so global ordering. So instead of forcing global ordering, which is a very hard memory, which is a slow memory, if you say it's a slower process, if you force ordering your logic, basically you're locking almost serially throughout the program. They biased themselves to do partial ordering. So also Volatile, the semantics of Volatile have changed and made sure that when you declare a volatile variable, it's guaranteed to go back to main memory, right? And it's no longer being stored on your thread local buffers. They are flushed every time you write. It goes flushes, and every time someone reads, it's retrieved from main memory. Now there are some performance nuances around it. You actually lose some performance by that, but we are assuming that you want that ordering in your system. And that ordering becomes very critical, especially in the multi-core systems, where you are running lots of threads and you do have lots of CPUs to take advantage of that. So, so the whole volatile concepts, redefining the volatile as forcing order within how memory is accessed, has made sure, has brought at least the happens before causality into the JVM. And that has given more, so that has actually saved, quote unquote, the order across the JVM. So data races are less likely because your memory model is busted. Memory model is now actually been fixed, and so you don't need to see data races if you have not introduced them, sort of, right? Then you see future task. How many have you? Most of you have probably used future task. So the last 5 years of programming in Java is so different from the first 10 years, right? Because now you have all these nice little cool collections. You have queues, blocking queues, and ways to use them. And so some of the new big data projects actually have started in 2005 and 6 and 7. So these are new code bases, and their code is, so if we occasionally look at code that was written in 2000, like Tomcat has about 400,000 lines of code. And then you look at the new code bases, which are doing much bigger tasks than a traditional Tomcat, have less than like 75,000, 80,000 lines of code. So 5x shortened code, much more work. The idea is they're using feature task and blocking queues, and all the new collections that have been invented after, which allow you to do a lot less code, and do a lot of runtime typing. But the reason this thing is here is that feature task actually uses simple counters, simple castable counters, or atomic counters, to take advantage of creating order. So, for example, if you know that, a simple way to think about this is if you know that A will happen before B. So, in other words, you're incrementing I. So you have I plus plus, right? So you're incrementing I. So if I goes from 1 to 2, you know that that's actually going forward. So let's say that's going forward in time. You can basically connect that series of events which are going forward in time with your time, to deriving your own time. So in other words, you're piggybacking on something that is guaranteed to go forward in time with your own logic. So in future tasks, you'd say, okay, I know that's going forward, so I can also increment my own thing. So in some sense, you're not forcing your variable to be volatile or your variable to be synchronized. You're just deriving forward motion by piggybacking on some other thing that's moving forward. So that's kind of the concept behind it. So iterators use this all the time, and that's kind of the reason that's plus. Look at JSR 133. That's a very common, that brought all the concurrent collections into the JVM. So here's another take. I don't know how well it shows. Take from, actually reminds me of the old-fashioned slides which we used to use present. But this is showing that a thread local on a, so this is comparing lock performance between lock and atomic integer. Right? So what's the performance difference between locking and using a reentrant lock or an atomic integer? I think the program here was a pseudo-random number generator. And so for high contention, a thread local lock is actually faster than than your atomic integer or reentrant lock. Where they actually exceed is actually in your moderate contention. So if you don't have contention at all, then you're better off with the other side. So it's kind of a taken from the concurrency practice. Brian Getz talk, so feel free to go look at it. Java util concurrent also has locks. So don't forget that Java util concurrent also has locks. It's actually a visual from IBM tool actually that does show JUC statistics. So there is a monitor even behind Java util concurrent. So don't assume that just because we have used Java util concurrent, locking is gone. Here's a Tomcat in production that we managed to catch. How the session manager locks under contention. This is actually real code. Went on to go and fix the hash map on the top, which is highly contended. So if you write your program, make sure you run it against a large load, high concurrency load, to see where your locks are. It's important to know as a designer where things could be, so it's not a surprise. We actually, the session standard manager, we actually patched Tomcat at that point, and that went away. When you actually look at the code, it's very trivial. You look at, once you know where the lock is, if you open the code, oh, that's a trivial thing, usually very trivial thing. Instead of being in production and knowing that you have only 30 threads that are working, this is a very easy way to do it. This is actually the ZVision tool from Azul guys. Non-blocking collections. Yeah, so one of the things that we realized is Amdahl's law actually trumps Moore's law. If you have a large single-threaded part of your program, Moore's law is not increasing megahertz anymore. It's increasing more cores, right? So Moore's law is still in effect. You're actually getting more transistors, but they're all parallel. So what we need to realize that if you're not going parallel, you're going to be in trouble. So we actually looked at an example of state, actions, and key value pairs earlier. If you looked at that object model, how an object is represented inside the word, the mark word, it was a state and actions, what to do, and a key value pair. So one of the key things that we learned trying to do concurrent programming is that if you can actually parlay your program to a state and an action, you're able to look at go back to finite state machines, the automata theory that we learned in our undergrad. If you go back to that state where we're looking at, okay, this is a state, this is the various possibilities for it, and these are the various values that you can move to. So once you come to that level of understanding of your program, multi-threaded programming becomes very natural. Otherwise, you're constantly looking at a code fragment and trying to see what variables to lock up, right? So, and that's a different way of looking at synchronization. Come up with parallelism requirements very early on in your coding practice. So then you can actually look at an unbuilt product in some sense and come up with an algorithm that would say, okay, this thing can transition this many ways. So in this case, if you look at a hash map, and we often do this as part of our new people when they join our company. We tend to ask them to design one that doesn't lock, right? So if you look at hash map, these are the four operations it has: get, put, delete, and resize, right? You need to store your data somewhere, right? So you have byte arrays. So byte arrays, of course, are the most inexpensive ones to start with. So let's use that as your data to put your data where you put in data. So you have a collection of byte array, and then how do you want to avoid locks? So you know there are some atomics in the JVM, and that's CAS provided by the hardware for you for cheap. And then there are so you want to use the CAS. So this implementation by Cliff Click actually uses no locks and no volatile. So that's a very good open source. SourceForge has this code. It's actually part of Cassandra. It's also part of a lot of other big collections that I've seen recently, where you can get a completely scaling, high scale with large number of threads. You get a lot of you get the throughput that you expect. What we found, so the crux of that algorithm was basically, okay, you have for the most of your reads. So if you're doing just puts, you don't actually need to lock for a long time. That's what the interesting thing was, unless your hash is broken or your collisions. But for the most part, your puts don't need any locks on the way. It's your when you're putting and getting from the same contended hash key, that's when you're actually trying to come to a lock, right? So if you use CAS, so that's the most contended part. The other part is when you're actually resizing. So if you hit the full limit of your byte array, you need to have a larger overflow byte array, copy this over, and then while you're copying over, you have another small segment which is critical section. So during your copy, you need to backfill your writes, and then use that overflow buffer, merge the two buffers. So in some sense, this is an interesting approach to doing collections. And actually, now it's very common to see non-blocking stacks, non-blocking linked lists, and so on and so forth. So the copy array, so this is the kind of the resize algorithm. So this is kind of pseudocode on the slide, but real code exists, and real code actually does speak very well and runs very well. So we've seen other parts of the system lock up because of this hash map, because it's really lock-free, scale-free. Okay. All right. Who has not seen Java overheads, right? have C versus Java wars rage pretty widely across different age groups of coding. So what is the cost of an 8-car string, right? All you wanted was an 8-car hello world, right? Not even world. And Java takes about 56 bytes to write hello world, right? That's a lot. So where does that go? It goes into the headers, the fields, and part of the headers that we talked about earlier, pointers, and then you have length. Actual data is there, right? So and then you still pad it so that you can. Of course, there are some optimized string representations and string collections, but that's what you're using when you're using a Java lang string, right? Tree map. Actually, tree map is a very popular ordered collection, right? So ordered set. Again, tree map has if you use the double tree map, the interesting thing is the tree map has this tree map $entry, which basically it's not amortized. So sometimes you use a collection, you amortize your cost up front. So if you used a kind of like a linked list, right? So you basically or an array, you actually basically the overall structure has some cost, and the actual per element cost is cheap. So after some size, you're okay using that collection. The problem with tree map is that you're using this tree map 40 byte array almost every time. So you get to a blow up of really 5x. So that's a large overhead. So think about what collections you use when you have smaller sets. So it's really, if you need the ordering, and sometimes using a real double-double, like a primitive double-double, is much faster. But if you need the ordering done for you for cheap, you probably have no choice but to use this. But maybe you can write a small function that can do it if your set is not out of bounds. So that's kind of the crux of this. If you look at memory profiles, so actually the average collection size is roughly 3. So one thing we did was study all the size of collections. But anyway, here's a memory profile. This is Cassandra. The core data structure for it is a concurrent skip list. And the concurrent skip list also has an overhead that's reasonably well amortized, but it is expecting ordering. It does ordering for us, and we kind of want it to order. But if you look at the actual, it's one of the top things in our heaps. So that's what takes the byte array. So it's used byte array for presentation. That's one of the top item there. So which collection do I go with? And so there are a bunch of, so if you're thinking about concurrency, Google Collections, NVHM, these are very common good collections out there. But watch out for per element cost. So if you write a small micro program, so in this case, you can actually get a rough idea, like a small, so before you jump to using a collection, of course write it, but make sure, measure it, see if the collection is growing out of bounds as you add elements, or if it's coming down to if you're amortizing your costs early on. So it's kind of a, so the trade-off is the collection actually per element cost or not? So that's kind of your big thing to look for. Primitives are cheap, but they can be hard to manage. So if you have a very large collection, then sometimes you do want to use a real collection as opposed to primitives. So, but the average collections are really very sparse, and they're roughly size 3. So for 3-sized collection, don't put a huge, big, large collection in there. That we jump quickly to serialization piece, right? So serialization has gone really on. I mean, Java I/O serializable is really slow, and historically it has been designed to be slow in some sense because Java expected things to move from one platform to another platform or any other platform, right? So they made sure that all the protocols are kind of everything, the entire object is flattened, and even information required, environmental information required is flattened. So you kind of take the whole thing across and deserialize it. It's really slow. So it's done true. It's kind of like true colors, true platform, right? So how can you do better? So if you use transient, you can ensure that certain fields that need to be serialized, that are the ones that you want, can be shipped across. So you don't need to flatten the entire thing. another, so the other externalizable. So if you use an externalizable, you can write your own, roll your own serializer. You can say, okay, all I need is the ID of the stuff stored in database. And I don't need the entire object because I can recreate it here. Right? If I need the ID, don't serialize everything and ship it across. So that's kind of your externalizable. You can create your, roll your own serializable. Now we'll hear the gory details of Avro and Google protocol buffers as we go forward. But this lack of good serialization at the core Java has led to almost the new evolution of Java software we're seeing, which is the Thrift, Avro, and Google protocol buffers based systems. And that's kind of the heart of where big data started again. Instead of suffering like the old WebLogic, WebSphere stacks of systems suffered the RMI core costs and put it inside their overall scalability challenge, the new structures gave up the old serializable and took on to this techniques. A common benchmark that's out there is the SerDes benchmark, and does put, if you look at the roll your own, is still on the top, the Java manual. And somewhere down here is Java built-in, really slow, like many times over slow. Thrift is somewhere here, protocol, Thrift, protobufs, Thrift, and Thrift compact, Thrift. 06 is actually much faster than 04, did some benchmarking recently as well. But yeah, it's across the board, right? Somewhere down here is JSON, which also is another common popular one. People use it more often than you expect. XML, another. So know the spectrum. This is actually the cost. So this we are measuring. This is actually a benchmark from GitHub, very reasonably common benchmark. SerDes benchmark. This is measuring the whole object serialization, transfer, and deserialization cost. So it's the full cycle. And some of them are better on allocation. Some of them are better on deserialization. So some nuance exists. Avro is somewhere here. Right? With Avro, so again, Doug Cutting has poured a lot of work around Avro. So if you hear him talk, any of the new recent conferences, definitely attend and know all the gory details of Avro inside. The crux of it is being able to separate your schema of your object from the actual representation in the serialization. So one common, and I didn't realize there was an easy way to demo it. One common thing I usually do is like dump a serialization, serialized hello world object and look at it and see what's inside. Right? If you do a hex editor and look at it, people actually have the entire object fields and see, and then there is the string hello world. So it's very, very insightful in the sense that if you look at the Avro dumped stuff, types are all runtimes. You don't actually have to predefine all your types. You don't have to predefine. The data is untagged, so you don't need to tag your data. So you can actually get it across without having to change. And all the field IDs are pre-assigned, so you don't actually have to manually assign. Manual assignment of fields is error prone, at the same time is also less effective. Right? But then you could ship from one JVM to the other JVM. That JVM might have a different version. So you're still prone to schema mismatches. If you had a schema mismatch, so if you came up with used one side of the data, the other side did not have the right schema, you could have a mismatch. So there are some issues with it, and since they are only runtime checks, you don't catch them during compile time. So all these checks, type checking is postponed to runtime, so you may actually catch it in real time in production, and so that's kind of one of the cons with Avro. But I mean, if you're using the Hadoop family of stuff or HBase, and there's a ton of good classes of programs that are using Avro. Google protocol buffers. So protobufs came along around the time when distributed caching became very popular. Everyone started writing their own protocol buffers and tried to reduce the copies. So here you decide you can predefine your entire message format in a .proto file. So if you look at this schema, you take a class every class you create a full proto. So once you have a dot proto, you can then generate the other side, the class, the model array. So the interesting thing with protocol buffers is you actually have all the types of the fields, just like a database would do, have the fields, field matchings. So you can basically, you ship the data just as key value pairs, and based on ID, recover it from the file. So it's a very very database approach, data-oriented approach to doing serialization and deserialization. Reasonably very fast, and so yeah. So there is Android uses protocol buffers across the board. Most of Google Java products, Bigtable and others, end up using protocol buffers in the back. Thrift. So Cassandra uses Thrift, and Thrift actually is pretty very layered approach. So in some sense, this is almost the closest to Java in some sense, because it actually does the entire from your client to server. If you shipped an object across, you would actually take it through the entire stack, just like you do TCP/IP, and ship the entire all the various layers of that across, and it's recreated for you on the server side all the way up the stack. So it's kind of separates the structure from the actual protocol and transport. So in some sense, it is very portable. At the same time, it does have that overhead. It does have all the layers. It does have T-socket and T-file transport, which you have to manage. It's new way of doing. So it wraps around existing socket, creates catch, and so it creates exception handling around it. But so it doesn't differentiate between socket or file. It's just transferring things across I/O channels. So it's really a clean and I/O protocol, expecting things to go across the wire out of the box. So there's no nuances around it. Right? Of course, so you could compact it, make it compression, so you get some performance over there. Still, regardless, it's a heavier system out there, but it is the most portable of them all. So. With that, we jump to the next fragment of this talk, which is UUIDs. So, how many of you have used UUIDs of late? Almost all of you. So, the good news is we don't use anymore the basic random call and create an ID and assume it's unique. You end up having to use UUID if you have used code recently. Turns out the default actually behind the scenes, so Lee Charles is the 128-bit, that's the actual definition for UUID. Actually, there might be one. Yeah. So a UUID is actually, if you break down, has these various nuances to it, right? So you have 4 parts to your to UUID, and so this is the classic. I put this function up here because the toString is the most common thing to call on your UUID. People create a UUID, then create a string out of it, and then use it in the program. It's a time low, time mid, and a high version and a variant sequence. This is kind of your telling you what definition of UUID you're using, and 4 is the one that we use for Lee Charles. So that's kind of this 4. Go back. It's so the basic, the default UUID is using SHA transform, and so it's expensive. Also uses, turns out, the default pseudo-random number generator, which is actually in the Sun JVM. It tries to get a seed for your dev urandom. /dev/urandom, even on EC2, is a file system call, right? So it will go to the VMware layers and make a file call. So if you're running happily in memory, your call for every UUID actually goes to the file. So you could disable it by saying EGD file does not a file name that does not exist will never go back, and does about 20-40% better because it actually uses the local algorithmic pseudorandom number generator, which is faster. But fast forward, people today use time UUIDs. Turns out time actually is a pretty, the current clock time is pretty good seed to start from, right? So using that to create your time UUID much faster. There are lots of alternatives out there. It's about 10 times faster because the time call is actually a system time millis call, right? There's an actually open source, a couple of these are open source projects, Quoton Coder or another pretty vigorous coder as well. And there's a call that you can look at these links offline. But these are pretty fast implementations for UUIDs that actually are used in some of the open source projects for big data. Here's a quick run on a regular program that it's actually output of perf_top. So perf has the package perf that we called out earlier actually has a program called perf_top, which gives you the breakdown how your program ran, and so it kind of gives you the kernel time on this one is much higher than the kernel time on that, and that's basically the JVM SO. Here's a SHA transform, kills your program. Summary: use time-based UUIDs where you can. It's much faster. It's a much well optimized program of Java. 4 times less kernel creation, kernel time, and so on and so forth. So definitely better instructions per clocks. Causes if you're on EC2, try and see that you don't. Yeah, go ahead.
There's no native JDK support for time-based UUID, correct?
There is no. Yeah, be useful to have that. Project Coin is initially had that. I have not seen the code come in yet, so yeah, useful. All right, so that's UUID's short section. Yeah, so the toString. So toString is a common call. So time-based UUIDs actually have a toString that's optimized. Make sure it's up fast. Right? So strings, toString to string theory. Turns out strings are. I mean, we could do a full talk on just Java lang string because we use it every day, and not until recently, byte arrays were not part. I mean, character arrays versus byte arrays. So up until a long time, it was character arrays. So byte arrays are in, and there's actually a new flag that was in that we found through benchmarking that just compressing your strings can actually do pretty good things to your memory. So strings are very compressible, right? So the classic LZA algorithms work very well on it. So there's a new flag that came up in very new JDKs. We've used some of it as reasonably well. Can't vouch for it because I've not actually put things in production with it yet. So, but it does give good performance benefits. Append performance. Append actually, anyone who has used open source portals like Liferay or other Java portals find that they actually have custom implementation for appends, or avoid appends completely. If you profile your code and reduce the number of appends, you find that your GC performance gets substantially better. And so there are a lot of nuances around append, and so strings and versus string buffers, so immutable strings versus mutable string buffers. A lot of different overheads for that. Google has a bunch of Guava project which does a lot of good work with joiner. So appends turns out, so they have a simple joiner with a lot of it joins text very cheaply. Turns out if you actually find turns out if you actually have null, so empty strings, turns out actually the checks for empty strings, if you actually instead of used a string called null, you actually get much better performance because the JVM actually goes through a lot of checking to see this reference is actually looking at null. So skip nulls and use for nulls. So if you use for null something default, you can actually get a lot more performance for your joiners. There's actually a splitter which also uses behind the scenes regex-like things, not using real regex. The Java lang string actually ends up using regex by itself, so which is a much more heavier collection to use. So So it's an interesting question, right? So if you have a string um, and you want to, let's say, so different implementers over the course of the last few years came up with different ways to stuff your strings. So the 64-bit string, for example, if you're mostly not filling up your data, 32-bit representation and compressing the rest of the part can actually get you a lot of performance. So one of the things that if you use any standard profilers, you'll find that the first thing they break on is Java lang string. And the reason is they expect an internal structure for your string. And the common nuances there is when you touch strings, especially when you depend on the internal structure of your string, you end up having to poke through the byte array yourself, and you're off on your own in some sense. So for the most part, it's encouraged to not touch the internal aspects and play with the byte array yourself, because when the global system array copies come and play, you're thrown by surprise. But that said, a lot of like I've run into this when Terracotta started using it. They expect a certain layout for the string, and you can actually, as a program, look at it and make sure you're using the right internal fields and play with them. But you see different results when you use a different JVM or switch your JVM underneath. But yeah, so that's the string internals. Depending on string internals is optimal if you don't change your JVMs often. Yeah, null references. This is a call from code from QCon last year. So with that, I would go into garbage collection. If you have any questions, this would be a good spot to stop. But it's also a good as we go forward, we'll see a lot more GC focused content. So best practices. Best practices for GC start with verbose GC. So oftentimes there's a misconception that GC logs, I turn on GC logs and GC problem got worse, or logging IO problem got worse. We looked at all these. GC logs are cheap, and they are cheap even in production. So be reasonably verbose at having them. Be reasonably, put your foot down if your ops team is not giving it. Yourself, feel free that we have benchmarked that part, and that's actually reasonably cheap. It's not coming in the way of doing GC for the most part, actually. There is a bit expensive ones, and those are here. And but that's when you're doing tuning, hand tuning, and then they're actually doing census for your object layout. So possibly for your question, a tool based out of the free list census can possibly derive what part of that object layout is strings. But it's an interesting topic. But turn on logs and turn them on very explicitly. So if we get back to the core of GC, there are so if you really want to understand GC, think of your app as in a very abstract fashion. Your app, when it's running, is doing a lot of allocation, right? And an allocation is creation of new objects, right? And then you have kind of your system-defined size. You have memory, right? So you have size, your allocation rate. So allocation rate is filling up your heap. So let's say you have 1 gig of heap, and you're allocating it 100 megs per second. You have 10 seconds of runway, right? The way to look at your size is if I did not worry of any GC, I can run this app till 10 seconds. So that's kind of like first principle, right? Then while you're allocating, you're also changing these objects. So there's what's called, so all the allocation and the mutations, these are all called mutators. In GC parlance, when you hear someone say mutators, that's your mutation. That's where your allocation happens. Now, not all you're allocating is staying there. So your live heap may be like 256 megs. So then if you have a 1 gig heap, you're allocating at 100 megs a second, you know you have 10 seconds before you run out of memory. You find out that some of these objects are dying while they are before even 10 seconds. So if, for example, your objects are dying at 500 at half the rate, you know that you're always having a live heap of roughly half your total gigs, right? So you have half 512 MB. So that's kind of your trajectory of how your objects are, how your memory is runtime. So there's a runtime equilibrium, 100 megs per second, their creation, and 50 megs per second they're dying. So you kind of have an equilibrium around half a gig, right? So if you, now that we've laid that out, now you want to make sure that you clean out this, the ones, so you'll only have half the heap free if you're cleaning up that 500 megs, right? So, and so that's where garbage collection comes in play. The garbage collection is trying to see which part of your heap needs to be removed and cleaned out, and trying to try to walk through the entire heap, have some kind of a root set, so you know these pieces are always alive. Your class loaders, your basic classes, Java, Lang, object, and the basic, the way you hear of permgen and stuff, right? So the basic classes and the classes around it, it traverses all of that, makes sure there's no, so marks all the GC YABL objects, so the marking part, and then actually cleans it out at some different algorithms, right? When it cleans it, there's different methods to do it. But while it's doing it, so let's say it's marking this heap, some of these collectors don't want you to change what is just marked. So let's say you marked this part, and suddenly you freed that part, right? So you want to hold out your mutators from doing things while you are at either mark, scavenge, or the final clean stage, right? The mark, sweep, and clean. Now, so at some minor portions throughout this entire GC cycle, you have to stop things from mutating, and that's where stoppages come. So the entire GC problem can somehow be translated into 3 core free principles, which is basically you want to sustain a very high allocation rate and keep it within the heap size you have given it at a very low pause times, right? So you want to give a low pause times and try and see what kind of size you want to put. So and try and sustain a very large live set and possibly a very large allocation rate. So that's kind of the 3 fighting parameters, if you will. There's a 4th parameter, and that's overhead of GC itself. So you want to, collectors don't talk about it, right? So because they don't want to advertise this part. There is a 4th parameter, and that's you don't want to have a very highly overhead GC. So for example, you don't want to have, so if you had 2 gigs room, so let's say you gave it 1 gig, and you created a 2 gig heap behind the scenes, then you have much more room to play with. Then your actual runway is not 10 but 20 seconds. So now you can actually play with how you do GC somewhat more reasonably, or you can put all of that in the other side, get very low pause times or stuff like that. So you can play it much more easily. The game is easier if you have larger heap behind the scenes. That would be a large space overhead. Or if you have lots of CPUs, or if you're able to run half of your CPUs, then you have CPU overhead. So behind the scenes, there's a 4th parameter, which is how much overhead can you, how much of CPU and memory can I take away? And that's kind of, so when you're tuning GC, you hear hundreds of parameters which are actually XX, that, XX this. The real parameters are here, and that's what you want to tune. That's what you want to understand of your application, and then your tuning falls into place, right? People tend to get to the hard introduction, and that's what's true for me as well. For GC is you come from these bazillion parameters that are changing their meaning every version, but what you want to understand is the core, your application load, your runway, how long your application will run, and what is an equilibrium size for your app, and what's the pause times you need. Maybe it's okay for you to pause once in a while if it's a batch program. Or maybe you're an online program and you just cannot live with anything large pause. And I've seen pause time requirements for some apps that are in the 5 milliseconds range. So for a large exchange, for example, every millisecond is actually almost equivalent of a denial of service. So there is pause time requirements at the lowest end, which is the low latency guys, to a pause time requirement where I'll just restart the JVM once it hits the GC. So I've seen both sides, right? So now sizing. So of course, some of this is simplified, and some of this is only applicable to the classic hotspot JVM, Sun JVM, right? But when I create a new object, so GC is actually, so now let's talk about XMX, right? The first X is introduced here, but the real, so if you got the last two slides, the rest of the slides are actually not so important. The last two slides were the most crux of the problem, because I mean you could come up with an algorithm which doesn't need to go through these details. So sizing. So the GC heap. So we took this 1 gig heap. We could have laid it out into different phases, right? So what this implementation is proposing is, let's put all young gen apps in one place. So this is the young gen, Eden and Survivor spaces. So it cuts the cake of 1 gig into 2 parts, young gen and old gen, right? So, and it's through some mechanism I'm going to promote them into the old gen, right? The assumption is that is a common assumption, which is infant mortal applications or objects, where basically they say that lots of your objects will die before they get promoted. So if you ran your collector on this one and cleaned it out very efficiently, you never need to worry about, so you can basically run 2 parallel collectors on each of them with different algorithms, and as long as this guy is very efficient and fast, you don't observe a lot of things fall over here. And since this guy, by definition, these objects in old gen have a lot more connections, the move from here to here would be much more expensive, right? So that's kind of the designer's ideal dream, right? Oh, I have these objects, all of them. So let's say we created that 100 MB, they all die instantly, like 1 second. We wrote hello world 100 times and vanished, right? In that case, they're instantly finished. So they come here immediately, collect themselves as garbage. Some collector just cleans it off, it's done, right? So when you're doing a new object, let's say you're doing this new string, it would be created here. So, or any object, you're creating it in the Eden today. So it's all your allocation rate is a function of this one. So if you looked at allocation rate and you want to amplify how quickly your application grows, like rapidly, that's your Eden size. So you want to amplify the size there, right? And this is XMN, by the way. So this whole size is XMN. Anything that gets created here overflows into a survivor space, hoping that it doesn't need to be promoted yet, right? But if you have very well cached behavior, let's say you have a bunch of well cached objects, they are guaranteed to go here. They're going to live longer, right? So when you create state that's very large or state that needs to be residing in your memory for long, you end up with a lot of promotion. So the dream that the JVM designers had, where all objects will die instantly or very soon, actually did not work out in reality. Code resides longer. Actually, class paths became bigger. We actually have much larger objects which are in your permgen. So there's another smaller space here called permgen, which was supposed to never be collected, right? Even that has grown to be very large. Everything has grown that you actually by default promote them these days, right? So if you use a default promotion mechanism, so there's another threshold, that so the tenuring threshold here governs how things go from here to here. But so the default ones promote very often and fill up the old gen as well, right? Sure, there is a adaptive size policing, which basically says, okay, I don't know if I made the right decision, change it for me, right? So actually the default is not, so the XMN actually clearly says this. If you set this to 256 megs, this whole thing would be 256 megs, and this would be the rest, right? That's actually a crisp cut. But often, and the default behavior is you set a ratio. You say, and there is a ratio, default ratio. If you set this, that ratio is overwritten. The ratio kind of tries to give you a small size. see how fast you fill up, and then changes everything with it with the same ratio. So it keeps changing it as you keep building the stuff. The problem with that is every time you change it, you basically resize. Not just that, you resize these survivor spaces with it, resize everything, and then shift objects during this process. So one of the things we found was that actually was detrimental to predictable performance. So one of the things we found, so if you're trying to find a predictable size, you want to cut this to, or do some experiments, that adaptive resizing actually causes, so the unexpected side effects of that will be seen in the pause times. So I guess by this time we are aware that pause times are what we are always trying to force to be small. So yeah, so there are some, so it's a heuristic and sometimes works, and it works very well when there's a lot of infant model objects. What we found in theory, in practice, is exactly the opposite, is that if you want predictable behavior from your collector and you're trying to do experiments to tune, setting the sizes up front right, and then tuning them to your workload actually is more predictable set of experiments than letting the adaptive size policy work for you. But on the other hand, people also use new, so in that, I don't know if I actually have a slide on that, but you can tune the ratio. So you can say min new size to max new size. So you can actually say tune this ratio from here to here and not beyond. So you can kind of say that don't go beyond 256 megs through that mathematics, but it's kind of reasonably tricky. So XMS and XMS, so MS is basically the starting size, right? So you start with, let's say you gave it a 1 gig, even though sometimes when you launch a 1 gig JVM, even though you don't have 1 gig heap, you actually pass, right? So you get a Java Dash version and you're like, what happened? Basically it launched with maybe 10 megs because it was a short-lived JVM. And so XMS is the initial size. So basically once you set that, there's no resizing for the entire heap. So the sum of all these is going to be always 1 gig. So it kind of cuts that out from the OS, make sure you have that full 1 gig. So when time comes to actually allocate it, it's not swapping. So that's kind of the, so that's the initialization size and the actual maximum size. So given that, so if you say that's set, so now you know you have 1 gig to play with and a new ratio of so and so. By the way, there are again the min and max ratios. If you use the new ratio or set them to the same value, min and max, you do get the same effect of an XMN, right, which is basically a fraction of it. And it's not, so if you put min and max, you get a auto resize for the new gen. But it's also a common, that's a common technique people use as well. Right. Next slide. So now that you've picked sizes, you get to pick a collector. There's a lot of them. And there is the Azul GC as well, which is not available in the Sun format, but it is in pure software now. Right? So a pretty fun book on the corner. Everyone have probably 200 copies, or maybe underestimating. There's very few copies of that sold, and very few copies fully read. It's a very academic, authentically academic approach to garbage collection. I've actually met a few people who have finished reading it, and Richard Jones is actually a good friend of the Azul community. We made him, but fundamentally, it gives you a very, very good ride and lays the land on what are the challenges involved in GC tuning, GC designing. So whether it's mark sweep and but anyway, so for the Sun JVM guys, these are the options, right? You have serial, parallel, old, and concurrent mark and sweep, and of course G1, which is still in experimental mode. For the Sun-like collectors, you have the Azul JVM, which has its own pauseless GC. None of the tuning before and after will be required because that's all auto-tuned. It is a low pause. There is almost sub-millisecond pause times on this at very large heap sizes. So it's 3-digit gig heap sizes, millisecond or sub millisecond pass times. And that's all on x86 hardware. So Azul started with a hardware solution. But the gory details of that we'll get to. I think at my last talk of the same topic, someone asked me, what is the secret sauce behind the Azul collector? And the quick summary I got was that's my mother-in-law's version of garbage collection, which is collect all the time. So full collect all the time. And there is no dishes, right? So it collects all the time, no pauses, you're able to allocate fast. But let's get to the crux of the meat here. Serial GC, so it's very serial, linear, serial new, serial old. It forces, when you hit that limit, when you hit the GC, you are seeing a stop the world pause, right? So then came along parallel GC, which basically does a lot of threads, parallel scavenge, so you parallelized collection. And then there is a serial old part, parallel old GC. So when you did the old gen collection, that was always serial, right? In the default parallel GC, very popular, very widely used, actually still widely used. Then came parallel old gen GC, which parallelized the old gen. CMS, again classic par new. So it uses parallel GC on your new gen, it uses CMS on the old gen. And really, when the concurrent market sweep fails, it does a serial old gen. So sometimes in your logs you see concurrent mode failure. That's when serial old comes in. G1 is actually G1 would probably be like 2005 version of the Azul collector, which basically uses pages as your. So it no longer believes in the infant mortality. It looks at pages and sees how densely your pages are, and picks the sparsest page and collects it, because that's cheapest, right, to collect. And then of course it deals with the problem of moving a popular page. So a popular object turns out to be connecting to every other object. So moving a popular object has a lot of nuances, and that's where G1 has its flaws. But picking a collector, the default I think is parallel, and CMS is a good option that's popular. Yes, so G1 actually is circa 1620 is available, but you still need to use the flag, unlock experimental options, and use it. So
it's just not. I mean, it was built for 1.7, but
correct.
It's now available in 1.6.
Correct. Stability is still a big challenge there, but of how it works and so on and so forth. There are some use cases where it should work with no flags. I mean, it should be. So G1 is designed with having zero flag tuning. So hopefully that works out for us. Reading GC logs is actually a topic in its own, and a very good topic actually. When you see these, right? So these are kind of this is so now we are getting into the nuances of CMS, which is kind of the most popular collector of the day. Parallel GC, I think, is well understood, and people know it still has a full GC in the serial old part, so it's reasonably well understood. Let's look at this one. So when you see full GC in your command line, in your GC logs, everyone knows that's stop the world, right? You have very poor. So, and then there is a stop the world part in the CMS, which is your initial mark, which is actually a stop the world, and that's what I was describing earlier. This is the initial mark through. The rescan and weak references and remark are also stop the world. So if you see those in your log files, look for promotion failures. So I tried to promote from young gen to old gen, and there was a promotion failure. That's a common time, and you actually do a full GC after that, right? You see. So the interesting thing is the CMS collector is actually reasonably conservative on its promotion, in the sense that if you have 10 megs of objects you're promoting from Eden into the old gen, it kind of it expects on an average one more of 10 megs is coming, so it makes sure you have twice the size in the old gen. So turns out when you do a 200 megs of transfer, you need 400 megs of already. If you've used half of it, it wants 400. It triggers a full GC on the old gen. So So that's the promotion failure. And then, of course, concurrent mode failure. It tries to collect the origin concurrently and then fails, and that there's a CMS origin collection. So this is how it looks like in real world, gory details. So this is the promotion failed, new promotion failed. And then, of course, a concurrent mode. This is a real use case from a customer. 5 seconds of full pause time has happened here in this case. Not that common. Now that part of my move from Azure, I see more of these in my customer base. But that's the full the GCPs. Perm. People look at this perm. You can disable collection of perm actually, so that there's a flag there. People don't use that. And then you can also tell promotion not to be that aggressive. Tuning CMS. So the next 3 slides are probably going to take us through tuning CMS specifically, because that's a common problem these days. Introducing a very new item there. Most problems of GC are actually solvable. The ones that are very hard to solve are actually fragmentation. And so if you get a quick idea of fragmentation, let's assume this room, right? When you came, one of the first person to come in, it was an empty room. So we could fill in tens of, or when friends of 4 each came, they could sit on a table. It's empty. Now, on the other hand, you actually have a lot more sparse spots here and there. So if a team of 4, a gang of 4 comes into this room, they would have to split because they don't have 4 consecutive seats. On the other hand, so that's the notion of fragmentation. You have fragmented this room. This actually is a very high residency, and thank you for coming again. But coming in at smaller, so if one each came, this fragmentation is not a problem for us. So if people came one, and since our objects are 1 seat each, those people can sit on those chairs. There's no problem. So fragmentation is a problem when you have large objects. Or irregularly sized objects are coming into your heap. It's definitely it's a big problem if that's happening. It's not a problem if you have uniform sized objects. So the crux of tuning this collector is basically to avoid fragmentation if you can. Fragmentation is the most difficult problem. So how do traditional collectors deal with it? They do a full GC. They clean up all the things, move everything, order them all into one side. Then you have large open blocks again. You can allocate again freely, allocate rapidly as well, right? So you coalesce blocks around you, so you can move people to the side, kind of get more space here, and create a size of 4 or 5. So in some sense, coalescing of memory blocks into and doing compaction cycles, and compaction cycles are all stop the world, and that's in the traditional GC collection, in traditional Sun collectors, and that's why fragmentation and compaction and compaction is not. So CMS doesn't compact, and so that's a big problem for CMS. Rapidly fast forwarding. There are other interesting heuristics baked into CMS. The CMS initiating occupancy factor, which is when do I trigger the old collector when I know the initial occupancy is this much on the new one, right? So that's so if you usually the default is something like 65, and that changes based on how you're so the fraction of occupancy. So you can set this and make sure that's what's used instead of using a heuristic, which is again adaptive technique, heuristic built for certain assumptions and doesn't work for the worst case. Min GC times, again a function of so size your generations well so that your min GC times are know that they're a function of your live set, not your total heap size. So you can have 10 gig, but if your live heap size is only half a gig, you're not going to be really a problem. Again, system.gc is another common. Someone actually used system.gc, the reason to come to this talk. So for them, if you use this flag, it invokes a concurrent system.gc, not a real stop-the-world GC. GC threads. So the trade-off between CPU and memory comes in around the number of threads. So parallel GC threads of size 4. So that's another common technique to get 4 threads running in parallel. The default is actually derived from number of CPUs on the system, and it's a pretty complicated way of deriving it, but that's what it is. So it falls off. What was found was that if you can't have 32 threads and get performance of GC falls off, and so there's a 8 is the kind of the flipping point. If you have more than 8 threads or 8 CPUs, you end up using n minus 5 by 8 as the actual. So kind of 16. Assume that you get kind of 16 if you have 64 threads. Something like that. So the strategy is to tune your min GCs, and then you can let a lot of allocation happen in the Eden. So that's kind of your. If you know your min GCs are low, then you have a lot of allocation rate possibility there. But that's so. This is your CPU trade-off. So you could do a lot more threads, and you're taking stealing CPU cycles from your application work to GC. So that's your overhead as well. Fragmentation. So you have an app that runs very well up until suddenly something happens, a knob turns and performance goes degrades. It induces. You try to do a full GC from J console, everything is happy, and you continue to run, right? So that's the classic fragmentation use case. We talked briefly in detail about this. So the real trick is that when you have basically this whole, if the gang of 4 did arrive here, this whole table is actually not available for allocation. It's considered round off error, and you kind of let to find it, you trigger a whole GC. So so if you use a compacting collector, fragmentation is no longer a problem, and that's where I was mentioning compaction, which is heavily avoided by all the collectors. The Azul collector compacts always, right? It's compact always, and a lot more interesting nuances. Very parallel, highly concurrent collector, so it does both generations in parallel, in complete concurrency. So kind of the window of actual pause time is very low. So the Eden is collected in parallel with the old gen, 2 completely concurrent collectors running for you all the time, and so and all the time is not triggered by events in the application, but it's happening continuously. So it's kind of the only compacting collector which proved the paradigm, which hit the nail the opposite side, which basically don't avoid compaction, do it all the time. So doing it all the time, we found that the pause times were actually very less, and then you don't need to worry about all the various parameters there. So promotion. So if you delay your promotion, so as you promote, you're basically landing your objects in this old gen page and corrupting all the pages at different paces. If you promote less, you're fragmenting less. So in some sense, that's kind of the real solution that people have found is to be able to build uniformly sized objects. If you used arrays or primitives, you have some control on that, but in Java parlance, it's actually very hard. Object pools were around for some time. Again, all of them have their own issues and nuances. So of late, and so the last few slides of this topic are actually topics of their own. We've seen a topic recently by Todd Lipcon from HBase team, who has done a complete talk after this, which is basically go off heap, right? So we'll touch a little of that. How do I build off heap? But so we've talked about compaction, stop the world, and why it's still yet unsolved on Oracle's Hotspot. They're working on it, but clearly this is the way to go on that front. If you're suffering fragmentation, talk to those guys. There's tools. Again, let's look at some tools here. JRocket Mission Control has a very good tooling on GC. You can look at the overall pauses, sum of pauses in different generations. You can look at compaction. You can get to the gory details of how long the mark took at every level. So this is probably one of the best tooling I've seen, and some people are actually going back to reusing the JRock machine control to use it to get kind of an idea on how your objects are laid out. You can actually double click and get what type of objects they are. So in some sense, it can still answer your question, but it's a derived answer. It's not a direct answer. It's a good thing to talk to your kit guys. They may actually pick it up. This was this is actually a thing in production that we visited, and basically application suddenly transitions to a back-to-back. It was reasonably well. You kind of think it's doing okay. With some stability, it suddenly goes back into that back-to-back. Nothing changed in the allocation rate of the app itself. So at somewhere around 40% full, it flipped into a fragmentation mode that said, although you thought you had half empty, it was not. You actually were full because of fragmentation. So you cannot use your free memory because you have way too many holes, and that's kind of the most common problems we see in GC are here, and these are the hard problems of the day. Yep. So this is actually from production cluster running Cassandra, I would believe. So again, there are some interesting tools here. Still, JConsole, Visual GC, logs. This is actually a tool that came around year 2000 by the team that works in the same academic as the GC Richard Jones book that we talked about. It's called GC Spy, which kind of gives you kind of your memory in pages and see how it's laid out. Kind of gets that. It's kind of worked for me on JDK 1.6, but I can't watch for it using it in production. But nevertheless, the code is out there. It's open source. It can be used. So with this, people have been talking, I'm sick of the GC stuff. Let me just go build my own off-heap. So the no-GC movement, if you will, like the NoSQL movement, or even the NoSQL guys are trying to build off-heap stuff, right? So crux of that off-heap, and I'm kind of giving you the initial tantalizing pieces. So if you really go off of this topic, off of this talk, if someone asks you, I don't worry about GC, I'm going to put it on outside the heap, you'll have something to communicate with those guys. But there are a lot more gory details there. The crux of that is actually a byte buffer, right? So the byte buffer allocate direct, and that was circa 2000, right? So very early on, Java kind of assumed that you'll create stuff outside your heap, right? So you can do a JNI, that's almost around the time of JNI, right? So you could create a slab of memory outside. It doesn't care if it's a file or it's really in memory. So you can put both a map file or actually chunk 16 gigs of heap, 16 megs of heap outside. The designers of JVM then at the time at Sun, assumed, and I'm kind of guessing here that outside the heap, now suddenly the JVM is not transferable, right? It's not as portable. So this was kind of always an orphan child in the notion of how you deal with it, right? So now you have these outside long objects that are going to be, how do I clean those guys so you don't have a memory control on it? So if you look at actual design, like Parnas, who is a software, anyone who's read software fundamentals and kind of the Boehm time, very early on, how do you build good program code? They came up with this notion of virtual machine. So the JVM is not the first virtual machine that was invented. The notion of virtual machine has been touted as the way future will be in 1970s and 80s, right? And the crux of that is that use virtual machine as a paradigm to build your apps. So then you can virtualize the file system around it, the I/O around it, the network around it, and so that's how the original concepts of programming models were created. And turns out one of the things that clearly said is that don't corrupt that view by adding a slight workarounds, right? Because then it's no longer a virtual machine, it's parse virtual, parse real, no longer apply the same paradigms or programming techniques of building this. right? And that's kind of the viewpoint of which JVMs have looked at going off heap, is that that thing is now no longer manageable. It's outside. I can't. I want to make sure it's very small. Right? So the first immediate thing that they did was make sure anything that's created outside heap is very small. But with the new, I'm going to build a big large cache outside the heap. You're heading into that territory. And if you're aware of that and manage that very well, you're probably fine. But that's the notion you are. That's where you are. So you actually have to. So anything else that's happening on that machine, which you have no control on, can be impacting you as well. So you can trigger swapping, for example, if something else kicks in. So there are other things there. But nevertheless, JNA and allocate direct allow you to do the dynamically load like a C program without having to incur the cost of pre-declaration like JNI. The question is this NIO based? Or yeah, yes. So the things got better. So whole NIO packages got much better in the recent versions. So we can actually even venture to do something like this. And but early on, that was kind of like the first use case of creation. Right? And JNA itself is again very clean. And if you run a simple program, you'll be impressed. Oh my God, I can actually run a hello world in C in the same JVM, and it kind of works. But really, it's not. There's no compile time declaration, so you will have potential runtime failure. So be aware of that. But it does work for limited use cases in the labs. There are people who are going that way. Even Cassandra is headed to try and do some off-heap analysis and see. The existing performance gains have not been as big yet. Let's talk about that here. Issues to consider, and so that's kind of the, how do I deallocate memory on this? The crux of that is that you resort to finalization. So finalizers, which basically are kind of the last gasp calls for JVM, that's where, so all the references to this outside heap are maintained in kind of like in a local in JVM site. So the clearance, so let's say even if we feed that memory, they need to come to this object which referred it and drop it off. This object is actually relegated to finalization, which means it's the last, so unless you have full GC, you don't actually see that memory freed up. So if you have frequent full GCs, and some people have worked around by creating system.gc calls periodically, then you can actually clear that out. So this is a very, so bug ID 44 means it's like early 2000s. Very old bug, has been there for a long time. And finalizers are one-threaded. So again, so those are the other nuances there. If you're aware of those, and so if you've done a gzip program, for example, in Java, you would have seen effects of something similar already. Like as you keep doing this, so if your gzip is not clearing it up, so if the JVM is not clearing up that program's memory use periodically, then you would see that you actually stack up behind a slow single-threaded program, and kind of cause the notion of a memory leak. Right? It's also it's a weak reference that's using that, which ends up being the finalizer. You can have a workaround to that. You have a max direct memory size, so you can actually limit the damage it can do if in case. And so there's a new flag that came in, actually a pretty recent flag, where you can set the max direct memory size, so you never actually go beyond that and cause the overall JVM. So yeah, the notion of having to trigger system GC to avoid in the first place if system GC kind of defeats it, but there are certain use cases where you actually need to go that route because of fragmentation. And hopefully, yeah, so this is the other, trigger a system GC and avoid a leak. Last part, which I kind of expected not to be here, and that's why it's virtually, if you got here virtually there, is turns out to be a long talk, right? So on virtualization, there are a bunch of interesting nuances to be aware of when you think about GC, think about Java. Thread priorities is one common thing, right? So thread priorities are very, scheduling becomes pretty much an art because the VMware is relaying your priorities for you all over again. There's a common ballooning driver. It's a common philosophy that's taught on how you manage memory in the VM world. And for JVMs, it's clearly the way to do it is to disable it. You don't want to get your memory reused to some other app while your app was kind of not busy, essentially. Right? You don't want to balloon your heap onto other processes. Time itself is an issue has been an issue. It's kind of been solved in the latest VMware ESX kernels and with the latest hardware. But TSC and the older hardware and older, if you're on an older VMware solution, it's very relative. So the counter TSC is not. So not all counters, not all performance counters are counters are virtualized. So you cannot measure things the way you would have measured on real hardware. So it's worth being aware of that is worthwhile. Not all EC2 instances are the same as well. So you get different performances with the same EC2 instance. So again, the latest Nihalem hardware gives you virtualization for direct path I/O as well as BTD and BTX. So, but if you're an IO1 app, be aware that if you're not using this, you have a substantially different performance. Basically, it allows you to bridge from your VMware guest OS, bypass the hypervisor, go directly to the network interface, and that's what this is doing. So if you have an IO-intensive app, try and use that if you're virtualized. So that's kind of the big picture out there. JVM still happens to be the most popular platform of the day. There is no question about that. Java may not be the app you're using to develop, may not be the language you're using to develop your app, but if you're using any variant of a runtime, the JVM is running most likely your app on the top. So different languages, but they're all trying to go back to using the JVM, which is pretty old and has matured as a platform. These are the kind of common heartburns at large scale, and we have touched on some solutions on those. So I think the question is 2 gig heap still the limitation for Sun GC if you have a low latency requirement, right? So if you have a low latency requirement, that is still the truth. We still have maybe we've seen it grow till 3.5 gigs for some workloads, but it's still the common case that small heaps are better than large heaps. But if you have a stateful app, for example, such as Cassandra, where you want a lot of live set, if you have a very large live set, we have found that larger heaps have been used by customers with periodic pause time, and we try to reduce that full GC occurrence once a day or once every 2 days. But reduced, so we are kind of managing the problem because the solution, while the solution is being worked on by Oracle, Azul, and other guys, we are waiting for those to become mainstream and use them for large heaps. But if you get a 256 gig heap, you know you can do a lot more today. I kind of expected not to be talking about GC in 2011, honestly. I was designer like you, building J2EE apps in 97, 98, and suffered GC in production. And I was like, wow, this problem needs to be solved, right? So, having put a decade of work on it, I kind of hope that problem is like gone, and we'll not be talking about this at all, and happily talking about stuff that's even more fun. Yeah, so the algorithms for working this out are in the works. I think in all the GCs, right? In all the JVMs and all the GCs, GNOME, JRocket, Azul, Sun, Oracle Sun. My guess is this problem is on its last leg, post and Oracle is a very customer-centric company, just like the others. So customers have suffered this problem. It's not a problem it's not a vacuum problem. It's not a problem looking for customers. It's actually a real problem. So there are two routes, and one that I present both of them. One was, do we go off heap and build our own? I think there are some JVM changes that need to happen to make the off heap work well, and that's the kind of like not relegate it to finalizers, but make it a mainstream thing. But the other side, so there are some designers who are going that route. The other route is wait out 1.7. Hopefully, GC is solved there. G1 is promising to do that, or maybe the Azul GC becomes so widely OpenJDK like that it can be widely applicable. But the algorithms are there. I mean, this field has been researched for decades, and there's the way we've kind of snuck ourselves into the first implementation, second implementation, and now we're trying to carry that parallel GC version into perpetuity. I think this problem needs to is very likely on its last legs. At which point, my guess is that the average, so I mean, memory has become infinitely cheaper, and it's very easy to get a 50 gig, 64. People want to launch a 64 gig heap, and so and you want to have it like if you're running something like a Volt DB, you want to have all of that in memory locally, and run it without a full GC pause. So my suspicion is that it's very likely going to be a problem that you shouldn't be even looking at, and JVMs are enough prevalent, even with the new Scala and others are all going to be JVM baked. So this problem is not a long-term problem. Yeah. So for the young people who often come and want to spend time trying to tune GC, I just tell them, don't worry about it. Patricia is one of them. Yeah, I mean that's how I started, and really having looked at the problem with different approaches, it's really an implementation problem. It's not a real problem. It's not physics. It's not definitely not rocket science. So, and I think that's kind of the learning of the Azul story, is that even without the hardware, we are able to sustain. Actually, without the hardware, we do better. In the notion of faster CPUs have actually helped, right? Faster L2s, and the new hardware has caught up, right? The Nihilms have the high QPI, have memory bandwidth. They do better. So, so all the architecture we proposed and kind of front run and test run, if you will, are the hardware of today, where you have 8 cores, you have very fast memory controller on chip, you get the high bandwidth. So if you have 4 such Nihilim chips, you have a pretty good system today. So yeah. So the question is, if I'm a mobile phone developer, and how do I tune my GC, or what collector can I use, and what's the world doing there? Is that kind of so small JVMs actually is it's a well understood problem. For the small JVMs, being able to tune GCs actually is a well people attacked that problem very early on, and it's actually quite solved the problem. There are different vendors. Metronome is actually IBM Metronome is very good at that, and it's actually also growing into being the big end one. But that problem, the real-time GC guys, which is the low-level, low-end, small, kind of the small-size JVMs, that problem is reasonably well solved. Even traditional collectors do very well at small heap sizes. So G1 kind of is also G1's goal is to go from 4 to 16 gig size, but if you're suffering GC at the small size, that's tunable, and that should be tuned. So so that problem you should actually look at the playing it through the logs, put it in this Excel spreadsheet, and find the right size, and you're probably done. Yeah. So the 256 meg and less size, that's actually a well understood problem, and there are a couple of different collectors. There's actually one collector GC company in Germany actually, which actually focuses just purely on that small GC, small mobile and Android environment GC. But traditional, all the other collectors should do a reasonably good job there. Parallel GC should probably work for you. All right, thank you.